Today, we are firing up the engines and breaking down one of humanity's greatest achievements, rocket propulsion. We're going to go from the simple physics that gets a rocket off the ground all the way to the incredibly complex machinery that makes it all happen. So here's our flight plan. We'll start with the absolute basics, the fundamental law of action-reaction. Then we'll get into the language of thrust by looking at the core equations. After that, we're taking a virtual peek inside an engine, exploring the whole family of different rocket types, and we'll finish up by marveling at the insane engineering that holds this all together.
Okay, let's dive right in with the big question. The one that every single rocket engineer has to answer before they can even get started.
I mean, really think about that for a second. Here on Earth, to move, we push against something, right? We push against the ground to walk or the water to swim. But out in the vacuum of space, there's nothing. So how in the world do rockets move? It's a real head-scratcher. Well, the answer comes from this beautiful, almost poetic law of physics. See, a rocket isn't pushing against anything external. It's actually pushing against itself. It works by throwing mass, in this case super hot gas, out of its engine at incredible speed. That's the action. And the reaction is all that gas pushing the rocket forward with the exact same amount of force. Simple, yet powerful. So how do we turn that elegant principle into a machine we can actually control? Well, that's where the language of rocket science comes in. To really design, build, and fly these things, engineers rely on a handful of core equations. And this right here is the big one, the thrust equation. Now, I know it looks a little intimidating, but it's really telling us two things. The first part is the core of Newton's law. It's how much stuff you're throwing out the back times how fast you're throwing it. The second part is what we call pressure thrust, and you can think of it as a little bonus push the rocket gets when its exhaust pressure is higher than the air pressure around it. Pretty cool, huh? And what that equation tells us is that engineers basically have two main knobs they can turn to get more power. They can either increase the mass flow rate, which just means burning more fuel every second, or they can increase the exhaust velocity, making the gas shoot out of the engine even faster. Either way, you get more thrust. So how do we know how efficient an engine is? Well, for that, we use a measure called specific impulse, or ISP. The easiest way to think about it is like a car's miles per gallon. A higher ISP means the engine is squeezing more thrust out of every single drop of propellant, mostly by getting a higher exhaust velocity. It's the name of the game for fuel economy in space. And that brings us to this absolute legend of a formula, the Tsiolkovsky rocket equation. This tells us a rocket's total potential change in velocity, a value we call delta V. You should think of delta V as the currency of space travel. Every single move, from getting to orbit to landing on another planet, costs a certain amount of delta V. This equation tells you if you have enough in your wallet to make the trip. But here's the thing. This equation also reveals a very harsh truth. Look at that mass ratio, your starting mass divided by your final mass. Because of how the math works, to get even a tiny boost in delta V, you need a huge increase in fuel. This is famously known as the tyranny of the rocket equation. And it dictates that to go anywhere interesting, your rocket has to be basically a giant flying fuel tank with a little tiny payload on top. All right, enough with the math. Let's get our hands dirty and move from the theory to the actual hardware. We're going to pop the hood on a liquid propellant engine and see what's going on inside. The journey that the propellant takes is, well, it's violent and it's incredibly fast. We're going to follow it from the storage tanks, through the pumps, into the injector, through the absolute inferno of the combustion chamber, and then finally out the nozzle as pure high-speed exhaust. Okay, so it all starts in these massive insulated tanks, which are holding cryogenic propellants that are colder than minus 150 degrees Celsius. From there, the propellants get grabbed by the heart of the engine, the turbo pumps. And these aren't just any pumps. These things are engineering marvels, spinning faster than a Formula One engine to cram those propellants into the engine against unbelievable pressure. Next up is the injector. And you can really think of it as a super engineered showerhead. Its one and only job is to spray and mix the fuel and the oxidizer in a perfectly controlled pattern.
If it messes this up even a little, the combustion can become unstable, which is a very gentle way of saying the engine could tear itself apart.
And finally, we get to the main event. The propellants ignite inside the combustion chamber. This is literally a continuous, controlled explosion. All that raw, chaotic thermal energy then gets funneled into the big bell-shaped nozzle, which brilliantly converts that messy, high-pressure gas into an organized, supersonic stream. And that is what creates the thrust that sends the rocket soaring. Now, that liquid engine we just looked at, that's just one type. Not all rockets are built the same, and engineers have a whole family of different engines to choose from, all depending on what the mission actually needs to do.
The two most common types for getting off of Earth are liquid and solid propellant rockets. And they really represent a classic engineering trade-off. It all comes down to a simple question. Do you need fine-tuned control, or do you just need raw, simple power?
And this table really lays it all out. You can see that liquid engines give you incredible control. You can throttle them, even restart them, but they're super complex. Solids, on the other hand, are simple and pack a huge punch, but once you light the fuse, that's it. It burns until it's done. And then you look over at electric propulsion. I mean, wow. The thrust is tiny, but that specific impulse, that efficiency, is just completely off the charts.
Just look at the efficiency numbers here. You can really see the massive leap that these more advanced propulsion systems offer. Chemical rockets are the workhorses that get us off the planet, for sure, but the unbelievable ISP of nuclear and electric engines makes them the absolute best choice for those long-haul missions across the solar system, where every last drop of fuel is precious.
Okay, let's wrap this all up by just taking a moment to appreciate the absolutely mind-bending conditions that a modern rocket engine has to not only survive, but actually operate in. First up, temperature. Inside that combustion chamber, it can hit 3,500 degrees Celsius. Let that sink in. That is hotter than the melting point of the very metals the engine is made of. So how does it not just melt? Well, it's thanks to some unbelievably clever engineering where cold propellant is actually run through the walls to cool them down before it gets burned.
And what about pressure? The chamber has to contain pressures up to 300 bar. Now, to put that into perspective, that is the same crushing pressure you would feel almost 2 miles or 3 kilometers below the surface of the ocean.
So when you put that insane heat and that crushing pressure together, what you really have is a continuous, controlled explosion. The fact that these machines can operate for minutes on end, perfectly balancing these immense forces to create stable flight, it's truly a testament to some of the most brilliant engineering in all of human history. So, at the end of the day, the crucial point to take away is this constant tension in rocket design between brute force power and elegant efficiency. And that leaves us with a really fascinating question for the future. As we push farther and farther out into the cosmos, what will the next great breakthrough in rocketry prioritize? Will it be raw power, or will it be long-term persistence?
Rocket propulsion is a marvel of engineering balancing extreme temperatures, pressures, and chemistry while minimizing mass. Modern engines like SpaceX Raptor, Methalux full-flow staged combustion, or Blue Origin's BE-4 represent the state-of-the-art, pushing specific impulse and reusability to new levels. Understanding these parts and principles is essential for designing launch vehicles, satellites, or future deep space missions.